Welcome to lecture 6 in week 7, which is going to be on logic functions representation. Now, we are going to first talk about what we've seen in the previous lecture on the Boolean algebra and what we've shown with our simple example of an alarm system logic circuit. Then we're going to focus on logic circuit to truth table conversion. We're going to talk about the general truth table structure and logic function representations. As you can see in the right of the slide, this is the example that we used for the simple alarm circuit, and this is an example of one simplification that you were asked to do, which was to build the circuit using only this particular type of an integrated circuit that has only NAND gates. And what we've seen together is that you can do things based on inversion. In general, you will be asked to produce a logic circuit based on some description, like the one you've seen in this example, asking to use only NAND gates. And what we plan to do today is show you a systematic way of how to approach this. So as I've said, you've seen how to do things, how to simplify things using Boolean algebra and your intuition. You have already seen how to build a circuit from a logic function, and you've already seen how to generate a truth table from a logic function. Let's see now how you can generate the truth table from a logic circuit. We're going to use again our simple alarm circuit as an example. So the first step is to just have a node somewhere of how the circuit looks like. In this case, we got the intrusion input, and we also have the smoke detection that they go through an OR gate. We also have the test mode, which, as you should remember, it goes through a negation gate. And then everything goes through a final AND gate. This is the initial version of our circuit. And this is the truth table that we're going to fill in. As you can see, it has the 3 inputs on the left side: intrusion, smoke detection, and testing mode, and the final outcome of the alarm here. Let's start with 0, 0, 0, which is the first, let's say, binary sequence you would put. If you follow the rules through all the gates, you will see that if you pass 0 for intrusion and 0 for smoke detection, the OR gate is of course going to give you a 0 as a result. If it is not on testing mode, then the other input to the final AND gate is 1. And as you already know, 1 and 0 gives you a 0 as an output. So in this first step, you've seen that the first row of the truth table, which is 0, 0, 0, gives you an outcome of 0 for the whole function. Now you go through all the steps one by one. The next one is passing 0, 0, 1, which gives you 0 as an output. And then again, do all the steps, and you end up with filling the truth table for this simple circuit. Just to remind everyone, if you have 3 different options as inputs, like you have in this example, then the number of rows that you would be expecting to have here would be 2 in the power of 3, or in other words, 8 different combinations, always starting with a series of zeros and always ending with a series of ones. Now, let us see how you can generate a general truth table structure. To do so, we're going to use again the same example and the truth table that you've seen so far from the previous step. We're going to take this truth table and we're going to add a few extra columns. The first column is representing the alarm as a function. And more specifically, the alarm is a function of I S, and T input values. For each and every row, we express A as a function based on the inputs. So you start from f of 0, 0, 0, then you have f of 0, 0, 1, all the way to f of 1, 1, and 1. So what is the extra column you're going to have here? It's a column of what we call the minterms. Take a minute and notice how we express minterms. As you can see, each of the minterms is the logic AND of the variables. But notice something peculiar. For each value which is equal to 0, we use the opposite of the variable. Let's take, for example, minterm 3, which is in the fourth row. Since the only input being 0 is I, we use the complement of I, and then we use the Boolean multiplication of I, of the complement of I with S and T, because for S and T you got 1 being given as an input. And of course you reach to the last row where all the inputs are 1, where obviously the minterm here will be equal to the logic multiplication of the variables without using any complements. So this is the second step, adding this row over here. And we're going to complete the picture by adding this last column. So in this last column, we put a sequence of all the minterms from minterm 0 to minterm 7. And of course it makes sense that the way that it's constructed, for the first row it will be 1 and everything else equal to 0. For the second row, only the second bit will be 1, and diagonally, as you can see, you get 1s here. Let's try to explain why this happens. Let's take minterm 0 as an example. Minterm 0 is 1 if and only if all the inputs are equal to 0. And that makes sense because we have constructed this minterm out of the complements of all the input values, exactly because the input values are 0. This minterm is obviously going to be 1 only for the first row, but for any other possible combination, it's equal to 0. And why is this? Because we are using a logic AND, which demands for all of its inputs to be equal to 1. Now, in this AND combination over here, for example, all 3 inputs are equal to 0 when it comes to the minterm 0 here, because we use the complements of the inputs. And any combination that you try, you will realize that M0 can be 1 only for the first row, and so forth. The second minterm, minterm 1, can be 1 only for this combination over here and 0 for everything else. So the overall alarm function is equal to 1 only for these rows 2, 4, and 6. And we know that because of the truth table that we previously constructed. Therefore, you can express the alarm function as the logic sum of these 3 minterms. Now, if we are more thorough on that, it's this logic sum where each term here is a logic AND of the 3 input variables. Therefore, you can call that as the sum of products. So just to wrap up, when we are constructing a general truth table using minterms, our ultimate goal is to come up with the sum of products. In this particular case, the sum of products looks like this. Now remember that we started from this logic function over here for the alarm. Now let's take the sum of the products. You can easily spot that the complement of t is the common term here. So if you extract it, you get this. And then by using the rest of the basic operations and 2 and 3 variable theorems, you will soon end up in the original alarm Boolean function. So, as you've seen in this example, the sum of products is an equivalent to the original alarm function you were given. And this is a methodological approach on how to construct a general truth table, which always gives you the function, the Boolean function that you want, in a form that we call sum of products. Now, as you may guess, just like we've done other times, we're going to show something which is similar, only using a sort of a reverse logic. Instead of using this time what we called previously minterms and a sum of products, we're going to use the product of sums, and as you can guess, something called maxterms. Now, unlike our previous example with minterms, here you see that you're using maxterms being equal to the logic sum. Every time that you encounter a 0 as an input, the variable that you're going to use is going to be in its original form. Whereas every time that you have a variable with a value of equal to logic 1, you will use its complement up until you reach the last row where all of the inputs are equal to 1, and therefore for the max term you use only the complements of these variables. Again, if you put the max terms in a sequence, it makes sense to see that on the diagonal you got only zeros and everything else is equal to 1. And this is because of this. Starting with the max term at row 0, this is 0 if and only if all of the inputs are equal to 0. For everything else, it will be 1. Which, if applied to all of the rows, it will give you a diagonal of zeros, and everything else equal to 1. It's the exact opposite logic of what we used for the minterms. Now, unlike what we did for the minterms, this time we try to find all the rows for which the output of the alarm function is equal to 0. These rows are 0, 1, 3, and 5. Or in other words, all the rows that were previously not chosen for the minterms. Therefore, the alarm function is the logic end of all these max terms, which obviously, if you analyze it, gives you a product of sums. Having that said, and as we've done previously, now it's easy to prove again that the original alarm function is an equivalent to this product of sums. So if you start here and you apply the theorems that we previously shown, gradually you will reach to the original function over here. To wrap up, we've shown you how to convert the original function to a product of sums, and before that we've shown you how to do it the same or an equivalent way for the sum of products. Putting everything together, we have shown a methodological approach of expressing logic functions. In this particular table over here, we've put both the minterms and the maxterms. This is for the maxterms and this is for the minterms, otherwise known as the sum of products that you have here and the product of sums that you have here with the maxterms. And after the end of this short video, you've seen how any combinational logic function can be written as a truth table, a sum of minterms, or otherwise known as a sum of products, a product of maxterms, otherwise known as a product of sums, or you can also represent these functions by using a list of minterms. So this is the sigma of I, S, and T, and these are the minterms that you use, 2, 4, and 6. And let's call this its complement, the list of maxterms, which is pi, which stands for the product of the rest of the terms. And in this case, we talk about maxterms, 0, 1, 3, 5, and 7. To make a short comment, both the use of maxterms and minterms is easy to understand. It takes some time on paper. And to better digest everything, let's see an example. Suppose you're given this exercise. Construct the truth table of the logic function given as this, which is the sum of x, y, and z for these minterms. Minterms 0, 2, 3, 4, and 6. The first thing you need to do is try to construct a table by identifying where the minterms will be. And they're going to be, of course, in rows 0, 2, 3, 4, and 6. Then what you do next is that you put the columns needed for all the input variables, x, y, and z, and you're going to have one column for the final result of the logic function. Now, because you're using the minterms, you know that the logic function should be 1 for rows 0, 2, 3, 4, and 6. And it should yield 0 for everything else. Therefore, by using the sum of products for this particular minterms, and by using Boolean algebra theorems, you gradually end up in this, which is a simplified form. Now, that was an example of using a methodological approach on constructing a truth table, and as a next step, we also shown how to extract a simplified form starting from the sum of products. Which brings us to our conclusion. As you've seen, several representations of the same logic function can be a Boolean expression, a truth table, a list of minterms, or a sum of products as we call it, a list of maxterms or a product of sums, and of course gate-based logic diagrams. You should be able to navigate between all these representations.